I'm Ben Smith, and this is an introduction to modelling. Since you're taking this training course, you're probably already working with a model, and you probably have a pretty good concept of what a model represents and how you use the model in your field of research. But to start this lecture, I was thinking we'd take a step back from that and think about the concept of model in everyday life. Models occur in many domains of society, and they usually are an idealized or a simplified or perhaps a downsized representation of something. And the purpose, of course, is to make us think about the real thing that the model represents. It evokes that thing, inducing us to perceive something significant or perhaps essential about it. And the model is there as a mechanism for simplifying that thing, maybe explaining it, communicating something about it that we maybe find useful. We can take a model train, for example. Even though this is a very good replica, we can see straight away that it's a model. It's not the real thing. We're not confused about that. But by regarding the train, if we happen to be interested in trains, it may induce us to think of the real train, and that creates some sort of pleasure or enjoyment. Here's another example of a model, a street map. Obviously, it's very much simpler than the city that it represents, but it's actually very useful. It has just the right degree of simplification, so we can use it, for example, to find the quickest route from where we are to somewhere where we want to go. It simplifies, it explains, it communicates, and it conveys something essential in the context of what we want to use the model for. We could even think about the human model in this advertisement here, clearly idealized. And the purpose here is to be a proxy for the viewer, the potential consumer of the advertiser's product. Perhaps we identify with, or in our vanity, we would like to see ourselves as the figure in this advertisement, and that might induce us to go out and buy the product. A very effective way of using a model. So these examples, I think, are although they have nothing to do with research, they do demonstrate what a model is and the way that we use a model also in research. It's a method of simplifying, explaining, communicating, and it's something that can be very useful. So models in science then have been around for a long time, even before perhaps science became a formalized activity. We think back to the early days where many people were living on the land and reliant on the land. It would have been hugely important for them to know where to find food, the situation in which you might expect to find an animal you are hunting or berries you wanted to pick, the physical situation or other conspicuous species or habitats or communities. Of course, people wouldn't have used those terms, but they would have considerable skill in understanding those relationships. So that's a kind of model, a mental model, depicting a relationship that's very useful, in fact, essential for us if we're living in prehistoric times or in past times where our ability to live off the land was very important. Some of this kind of knowledge started to be discussed, thought about, depicted in a systematic way in the time of the early Greeks. This is Theophrastus, who lived 3 centuries before the birth of Christ, and he wrote some of the first, what we could call, botanical textbooks, describing morphological features of different kinds of plants, relating that to the utility of those plants, thinking about the climates, the soils, the topographic situations in which those plants were found, which of course was useful information to those that use the plants, again, as sources of food or fiber, what we might call ecosystem services today. So these are actually models. They are a simplified way or a systematic way of thinking about relationships, in this case in nature, that are useful to us for our survival and well-being. So the roots of models in science then are related to the concept of the model in general life. And again, we're talking about an idealized or a simplified representation. It may be conceptual, it may be mental, it may be more or less formalized. But the purpose again is to describe, explain, or allow us to study that real world phenomenon through the ability of the model to simplify, generalize, to find the essence of that relationship, for example, where we find a plant that's useful for us as a food source. Models also relate very much to what we call the scientific method, the method that I'm sure that we all are using in our research to try and advance knowledge. So I'm sure you're familiar with the scientific method, but let's walk it through. Really, this was a method that was described and formalized and promoted, I guess, by Galileo in the 1500s, 1600s. And the core of the scientific method, of course, is the experiment. And we all know that the experiment is a method or a procedure, the purpose of which is to test a hypothesis. And what's the hypothesis? The hypothesis is where we bring together knowledge we have about some subject of interest with some new observations that we've made that lead us to propose something about how that thing that we're observing works. And so it's a combination of knowledge, which comes from a broader body of knowledge, we could call that consensus knowledge or the state of knowledge, with something new that comes in, the observations, the data that we have that lead us to propose something additional, something that isn't yet consensus knowledge, and that we then are able to test through a systematic procedure that enables us to establish whether the hypothesis is likely to be supported or not, namely the experiment. And the purpose of this whole process, the scientific method, is to advance that body of consensus knowledge by adding some new knowledge through the hypothesis we pose and the experiment to test it. So this business about bringing knowledge that we already have with new observations, new data, and formulating a proposition is basic to the scientific method, but it's also the essence of what a model is in the research context. So this is really where modeling relates very closely to research methodology in a broad sense. So we carry out our experiment, we test the hypothesis. We're very pleased if we find the hypothesis to be supported. We can then make an inference about the thing we're studying that creates that new knowledge, and perhaps not through one single experiment, but through the same kind of hypothesis being tested with new data by ourselves or others. Eventually it can come to become part of that body of knowledge that's established and that we accept. And so science advances, the frontiers are pushed forward. Of course, we might equally be unlucky and the hypothesis is not supported by experiment, in which we go out and we collect more data, formulate new hypotheses, and the process goes on. The scientific method we all use, whether we are doing it consciously or not. So in this sense, the model within our methodology is a framework for integrating knowledge and observations, novel data, to pose questions that we then test with the experiment. So hypothesis and experiment, we can see for this, are very closely related concepts in research. Let's make this concrete with an example, and we'll think about building a model of the albedo effect. I'm sure you're familiar with the albedo effect. If we are wearing dark clothes in summer, we can get very hot. And why is that the case? If we wear lighter clothes, we don't become equally hot. So we can formulate a simple model about that, which says something like the darker the surface, the more sunlight it absorbs, and the warmer it gets. It absorbs the sunlight, it seems to heat up. Of course, the albedo effect is important not only for choosing the clothing you wear on a hot day, it's an important part of or driver of the climate system. And we know that dark surfaces absorb more sunlight. For example, a forest will absorb more than a grassland, or in winter time, a snowy landscape will remain cooler than it already is by reflecting the sunlight that comes in to a very large extent, as we can see from this satellite photograph, the albedo effect. So this simple statement, the darker the surface, the more sunlight it absorbs, the warmer it gets, is a kind of model. It's depicting a relationship. It's kind of a simplification of all the different aspects of what's going on with the physics of when radiation is absorbed and converted to heat. But nevertheless, it captures the essence of what the albedo effect is. We can get a little bit more systematic, and we can depict the albedo effect, for example, in a box and arrow diagram like this, a conceptual model. It has a couple of inputs. The albedo is a kind of, we could say, a parameter of the model. It tells us something about the reflectivity of the surface. The surface absorbs shortwave radiation from the sun. That creates a store of energy, which is converted into heat, and that raises the temperature. This is a conceptual representation of the statement above. A formal way of representing the albedo effect is through this equation. It's the Stefan-Boltzmann equation, or one way of formulating that equation. It's a full mathematical representation of the albedo effect. Each of these is a model. It's a model that can be expressed simply as a mental model, a simple verbal description, or as a conceptual model, a little bit more systematic, a little bit more formal, a little bit more specific in terms of what's going on, or a mathematical model that is an exact representation of the physics of it. So these are all models with different levels of specificity. I think when a lot of people think about models, maybe not you, because you're working with models already, but if you talk with your non-science colleagues, or even your science colleagues who don't work with models, about the work you do, and you say that I'm doing some modeling, using modeling as a method, maybe the first thing that comes to mind for them is this, the nightly weather forecast. And indeed, what we see here is the results of building and applying models, namely a forecast of what the weather is going to be doing today and tomorrow and for the next week or so, a weather forecast. This is modeling for forward prediction, and it's certainly one useful way of using models, but it's far from being the only way. Within global change science also, the IPCC process of predicting the future climate, projecting the future climate, very much a model-based exercise. It's about looking forward into the future and making some predictions that can be used to guide policy and so on. Gets a lot of limelight, a lot of attention. And again, when we think about models, the first thing perhaps we think about is looking forward into the future. Certainly models can be used that way. There's a lot of quality work involved in it, but it's really only one way of using the model, or one way of using models, and it's perhaps the mode of application that is least aligned with the core goal of research, which is to advance that consensus knowledge, that underlying knowledge we have about how nature works and that we seek to advance through research. So there are other ways of using models. So let's look at those. So yes, we've already said project future changes and consequences of those impacts of climate change on ecosystems, extrapolating beyond the data we already have into the great unknown of the future, or it could be the unknown of some other place where we don't have data. So extrapolating beyond the domain of the measurements we have is one way of using models, like the nightly weather forecast, like the IPCC process. What else? Kind of related to that, we can scale up. We can make measurements at certain points in time or space, and we can extrapolate beyond that using models, scale up findings, perhaps from local studies, case studies, to a region, to the globe, to spatial extrapolation. We can characterize uncertainty. We can look for what sort of patterns are robust versus which are uncertain and maybe in need of more data to constrain that uncertainty. We can use models to ask why questions. We can look at observed relationships between y and x, or between y and x1, x2, x3, and we can try and understand what mechanisms, what processes are behind those relationships to look for causality. Then we're attributing observed relationships and patterns to underlying drivers and mechanisms. Models, in a way, are, particularly more complex models, are performing a kind of synthesis. Given that, remember the slide about the scientific method, we're bringing together the knowledge we have with new data and synthesizing the state of knowledge. We can identify gaps. We can generate hypotheses which could be used to collect more data to guide empirical studies. And models also very much, think about the IPCC again, can be used to communicate scientific evidence to end users beyond, outside the domain of science, societal end users, decision makers, policy makers. And we could make this list longer, but this covers many of the ways in which models are used, certainly in ecosystem science. And something we can note is that actually, as we go down this list, and remember we started at the top with maybe the first thing we think about projecting future changes, but as we go down, there's an increasing potential to integrate modeling with measurements and data and experiments with empirical studies. As we go down also, we are tending to go from using the model to address what questions, what will the global average temperature be in 2050 and 2100, to why questions. Why are satellites seeing an increase signal of greening across the mid and high latitudes of the Earth? What's going on there? What are the underlying mechanisms for that? As we get down to the bottom, we get into practical questions. How questions? How can I adapt my farm management in order to increase the amount of carbon in the soil? And models are very, very useful for both these phenomenological kind of what questions to mechanistic why questions to practical questions about how. So let's move on to talking about the land carbon cycle. So the carbon cycle is an emergent property of ecosystems, an ecosystem or the ecosystems of the Earth, depending on the scale that we're talking about, of course. So the key word here is system. We're getting into talking about systems. And what is a system? It's a group of distinct but interrelated elements that are considered to comprise a uniform whole. So we're thinking holistically about some phenomenon that has different elements to it. And those elements have linkages between them, interactions, or very often flows of something, flows of carbon if we're talking about the carbon cycle, flows of water if we're talking about the hydrological cycle, flows of capital if we're talking about global trade systems, for example. And the key characteristic of a system is that through this holism, through these interactions, which can also include feedbacks between the elements, the system can exhibit features of its of its behavior, of its structure, that can only be understood by understanding the interactions and the relationships of the elements. So this is the domain of systems theory, general systems theory, that was formalized in around the 1960s, particularly by this character here, an Austrian scientist, Ludwig von Bertalanffy. But the kind of thinking has been around in ecosystem science for a long time, even going back to at least the 30s, and the seminal work of Tansley, whose view of nature was that if we want to understand the interactions between the organisms that comprise communities and ecosystems in nature, we need to understand how they're impacted by, but also how they affect their immediate environment, the air, soil, water that they occur within. So the interactions are mediated by those changes. And here the elements, of course, are the organisms themselves, but also components of the physical environment with which they interact. And there are exchanges going on, exchanges of energy, exchanges of carbon, exchanges of water, exchanges of nutrients. And that makes it a system, and we choose in ecosystem science usually to study ecosystems as a system, recognizing those elements that are interacting and the flows between them. And therefore the models that we use in ecosystem science, and certainly the ones that are the focus in this training course, are a particular class of models that are system dynamics models. So this means that they adopt a stock and flow structure representing compartments of the ecosystem, such as organisms, such as soil carbon pools of different lability, and the flows between them. They are structured mathematically in terms of time-dependent equations, difference equations that represent changes in the sizes of the stocks of the ecosystem compartments on a discrete time step, generally speaking. That's the case. Thus, the equations are describing the fluxes, and they're also expressing the processes that are responsible for the fluxes that link the pools of the ecosystem. And those fluxes are already mentioned, could be expressed in different currencies of energy or matter. Of course, when we're talking about the land carbon cycle, at least one of those cycles is the cycle of carbon. But many models also include interlinked cycles of, for example, water, nutrients, nitrogen, phosphorus, silicon, and so on, or energy. Another important characteristic is that the system dynamics model is formulated in such a way that the change in the fluxes in each time, or the fluxes rather, in each time step balance the changes in the compartments, also allowing for any imports or exports, for example, of carbon to the system. And this means that the system upholds mass balance, which is a very important assumption, and you'll learn more about in this training. Ecosystem models we use today have probably a common ancestor in the work of the Odom brothers working in the 60s and 70s, and a classic study of an aquatic ecosystem in Florida, Silver Springs, where this kind of diagram showing the energy flows, chemical energy, bound to biomass and to detritus and to particular and organic carbon in the water, is the currency of a stock and flow type representation of this ecosystem. So that's an overview about modeling and where we're coming from conceptually and historically, up to really the state of the art in how we use models in ecosystem science and for modeling of the land carbon cycle. The final part of this lecture is going to discuss a little bit about how we practically work with models in research, what the steps are. So we're talking about the modeling workflow. Again, it's the scientific method. We're performing science. We're trying to advance the frontiers of knowledge. And we do that by posing questions. You can call them hypotheses. And of course, our goal is to arrive at an answer. And modeling can help us to do this. In effect, we are formulating models and using them to perform experiments by bringing the model, again, remember, representing a combination of knowledge we have and questions we pose, hypotheses we pose, bringing that together with data in some form, constituting, in a broad sense, an experiment. So what are the steps to that? Well, first of all, we need to choose a model, or perhaps build a model, or perhaps take a model and adapt it to our particular question. Ecosystems are complicated. The models that we use to represent ecosystems in modern research are pretty complicated. So usually we're about choosing and possibly adapting a model. It's very rarely that we have the opportunity or that it would really make sense to try and build a new model from scratch. But nevertheless, we need to choose a model that matches our question. And there are several at least dimensions to that. The next step, having chosen a model, is to set it up for the experiment and make sure that it's doing the right thing. That's verification. A model may very well need to be calibrated to the particular context in which we're applying it, to the particular data we have, particularly the data that's extrinsic to the query that we wish the model to address. Validation, sometimes people prefer to say evaluation, but we need to establish that the model is behaving in a way that fits the data, that's representing the phenomenon we're studying, such that we can trust the model, such that its predictions are credible. And having gone through all those steps, we perform the model experiment and we get some output, and based on scrutiny of the output, we come up with, hopefully, an answer. So let's go through those steps and some aspects of what it's all about. So beginning with choosing the right model for the question. Modelers sometimes like to say that the model should be as simple as possible, but no simpler. And what do we mean by that? It means that, remember that the model is there to capture the essence of the system, to help us understand the system by focusing on the essence in some context, and that context here should be the question that we're posing. So that means that the model should represent the dependencies, the interactions in the system or between the system and the drivers of the system that are behind the question we're posing, behind the hypothesis that we're testing with our model experiment. But ideally, it should be, in other respects, as simple as possible in order to allow us to understand the answer. The purpose of the model, again, is to simplify, to capture the essence of the phenomenon that we're studying. In ecosystem science, scale tends to be very important. Finding a model that matches the question that we're asking, that matches the context of our study in terms of the temporal and spatial scale that comes with the question, is very important, because we do make assumptions when we formulate models about the scale at which the model is to be applied. And we can also note, again, that different models may be suitable for addressing different kinds of question. Phenomenological question: how does Y relate to X? How will the temperature change in the future due to rising CO2 concentrations globally? A phenomenological question may demand a different kind of answer from a mechanistic why question. Why does the land surface appear to be greening? What are the mechanisms behind that? Or how questions, which might be more management oriented. What can we do? What can we tweak or change within the system to achieve a certain outcome? So just focusing on one aspect of that and thinking about scale. So the ecosystem is a concept that could be applied to anything from a local plot to the biosphere of the Earth, the terrestrial biosphere, let's say, is all an interconnected ecosystem, interconnected through, not least through the climate system. And at each scale, we have a range of processes that are important in governing the dynamics or the shifts or the responses to drivers at those scales. We go from physiological processes of organisms, organ scale, even molecular scale, respond very quickly to populations of interacting individuals, competition between different functional groups, different species, to landscapes with spatial interactions, and ultimately we get to time scales at which evolutionary processes occur. We tend to call the fast responding processes the function of the ecosystem. The longer term processes are about changes in the structure of the ecosystem. And of course, we need to choose a model that accounts for those processes that are relevant at the scale that we're studying. Very different if we're looking at a soil sample in an incubation experiment, to a field plot in a forest, to a landscape, or to the global scale that can be the target of ecosystem modeling as well. Verification. Verification is ensuring that the model does what we think it's supposed to do. The model that you work with is probably a piece of computer code written in R or MATLAB or Python or C++ or Fortran. You call that the model. We call that the model, but it's actually, strictly speaking, not the model, but a solver of the model. The model itself consists of the mathematical equations, the algorithms, and we set up some computer code that's designed to calculate the output given the inputs that we throw at the model. And we need to be sure that those two things align: the actual model, which is the equations and algorithms, versus the solver, which is our piece of computer code. So that's verification. Confirming that the technical implementation, the source code of the model, correctly solves the model. That's not always necessarily easy to do. We typically don't have the analytical solution, for example, of the equations. Usually the system is too complex for that. Otherwise we could run the model, compare it to the mathematical solution, and ensure that they meet. But it can also entail things like, for a start, does the source code compile? Are there bugs that prevent it from even compiling? Does it execute to completion without crashing? We can also look at benchmarking. We can use relationships between an input and output that we know from previous work, from the work of others, perhaps from other models, from studies in the literature, and see whether the model seems to fit, roughly speaking, different benchmarks. And usually that can give us some confidence that, yes, the model is doing what it's supposed to do in a more or less technical sense. Calibration is a very important topic and very central to this training course, as I'm sure you realize. Because we're working with a system dynamics model, we have different elements, different processes represented. We sometimes call this a bottom-up model. We have different processes that we kind of join together like Lego to build the holistic view of the ecosystem as a whole, the conceptualization of the model. And this means that there is the opportunity to calibrate processes individually based on measurements of those specific processes. We can't do that for any process, but we can do that for some processes that can be adequately studied. For example, in a laboratory experiment, an example of that would be photosynthesis, probably the best described single physiological process in modern models of terrestrial ecosystems. And we can measure photosynthesis, so we can measure the gas exchange of a leaf and relate that to controlled conditions in terms of what we know are the drivers of photosynthesis, like leaf area, insolation, temperature, humidity, and so on. So we can do something like this, very simple empirical photosynthesis model here that we can construct through fitting a regression line to measurements of CO2 uptake and incoming sunlight Typically, calibration would be more complicated than that, but that's a simple example. Calibration gets much more challenging when we're talking about emergent properties of the ecosystem. And an example like that for the case of the land carbon cycle is the net ecosystem exchange. As you know, that's the balance between uptake of carbon, GPP or photosynthesis, and the release of carbon, which is the result of a bunch of different processes down the ecological cascade of processes like phenology, litter production, decomposition. At large scales, we have things like wildfires and their emissions, perhaps land use change coming in. So NEE, depending on the scale of the model, is a much more complicated variable, not dependent on a single process. And that makes it more challenging to calibrate. For these purposes, we have data assimilation, of course, an important focus of this course. We can use Bayesian methods, Monte Carlo, parameter estimation methods to calibrate multiple parameters based on observations, for example, of NEE or some other emergent variable that the model strives to predict. Validation is the next step, and it's a bit of a semantically fraught area in modeling. You'll sometimes have people tell you that no, you can't validate a model because a model can't be true. Validation implies establishing truth, and a model can't be true by definition. And that's a good point. Box wrote this in 1954. There's no need to ask the question, is the model true? The answer must be no. The only question of interest is the model illuminating and useful? However, it's a bit of a semantic thing. So we can redefine validation in the sense of modeling to mean that a model that is valid is suitable for addressing the study question. We have enough confidence in the model, in the representation of the model, of the knowledge that we have, that established consensus knowledge. And the model works. We've verified that it works technically, and we now want to find out whether it's suitable for addressing the study question in the sense that it fits observational data and patterns and relationships. And there can be several aspects to this. It's about the sensitivity of the outputs to inputs and parameters. It's about the parameter uncertainty, something that you'll be learning techniques to characterize in this training course. It's about the structural uncertainty, whether the model represents key processes, interactions, and feedbacks of the ecosystem in a way that is adequate for answering our question. Doesn't need to be perfect, shouldn't be perfect. The model's a simplification, that's the essence of it. But it should be adequate in order to say yes or no to the question or the hypothesis that we're testing using the model. It's about bias and error in the output of the model when we compare it to observational data. And when we perform validation, we're characterizing all of those things and judging whether the model is still useful or valid in the light of the results for addressing our question. So, classic example here, a scattergram plotting some model predictions against observations here for evapotranspiration and GPP. The blue line is the line of perfect agreement. We usually call that the one-to-one line, relating the model predictions to the observations we have for the same points in time and space. If all of the points fell exactly on the one-to-one line, we'd be absolutely astounded. And we don't expect that, but we do hope to see that the points fall fairly neatly with a little bit of scatter around the one-to-one line, meaning that the model is not biased and that the errors are sufficiently small. What's sufficient? Largely a subjective question. Depends on the question we're asking. We can use metrics like the root mean square error to quantify the degree of model error. There are other methods of looking at model bias, how the bias changes in different parts of the domain of the drivers of the model. But this is the sort of thing that we do, among other things, when we are validating the model. So next comes the actual model experiment, and because we're working with dynamic models, by definition, ecosystems, system dynamic models changing over time, the system evolves and that affects the output. And therefore we need to think about a simulation protocol that makes sense. So when we design a model experiment, we're thinking about similar steps to if we were designing a field or a lab experiment. And those elements are that there needs to be a control. Typically, we call that baseline in the model. We're looking for deviations from the control as we apply some treatment. What's the treatment? It's a change relative to the control in something that we want to see a response to in the predictors of the model, the drivers, or also the assumptions which could be inherent in the structure or the parameters of the model. In some cases, the treatment of our model experiment we call the scenario. And the result of the experiment that we're seeking to establish and to analyze is the change or the difference in the output of the model under the scenario condition relative to baseline. So just like in a field or laboratory experiment where we apply a treatment and perform measurements to see how the treatment affects the thing we're studying relative to the control condition. The simulation protocol is the rules for carrying out the model experiment, or the procedure for carrying it out. And it involves things like the input data we use, for example, on the environmental drivers, the time step that we use, maybe inherent in the model choice we made earlier on, the spatial domain, are we applying the model to a plot, to a region, a country, across a grid covering the ecosystems of the world. And we might look at some specific time slices to compare the baseline, perhaps pre-industrial conditions might constitute our baseline, and the scenario, which might be looking at a hindcast of the last decade, or it might be looking 100 years into the future or whatever. So the temporal period of analysis when we look at scenario versus baseline, treatment versus control. And so, for example, we might set up a future climate experiment with an ecosystem model, a land carbon cycle model, something like this. We have a long spin up where we force the model with constant or recycled and trend-free climate data, environmental forcing data. And the purpose of this is to establish an equilibrium in the state of the model by the end of the spin-up. We want the compartments of the ecosystem, the carbon pools, for example, in the vegetation, and the soil to be in a dynamic equilibrium with the trend-free forcing. And often that can mean that we, because of the residence time of the carbon in those different pools, it may take us hundreds or even thousands of years to get through the spin-up, unless we have some trickery to get to the equilibrium quicker, and that's something you'll be studying in the course of this training. We might follow the spin-up with a period where the forcing is based on recent history, for example, going back to the Industrial Revolution. And the purpose of this is because ecosystems have significant lags which are caused by the dependency of some of the processes on the current state. As the state evolves, that affects the output of the model, and we need to take that into account. So typically we might have 100 or 150 or even 250 years of forcing with, as far as we know it, the climate and atmospheric CO2, nitrogen deposition perhaps, which are the environmental drivers of the ecosystem cycling over historical times. And then in this setup, looking at a future climate experiment, the last part of the simulation protocol covers the future scenario, where we might take an RCP 8.5 climate projection, for example, to force the model. And so that brings us to the end, and some take-home messages for you. Oops, there they come. Whoa. So, take-home messages, what I hope you've gotten out of this lecture. Models, I hope that we are able to think of them now as being an inherent part of the scientific method that we all use. What they do is they provide a framework to integrate the knowledge we have, that consensus knowledge that we're confident in, with hypotheses that we might wish to pose based on novel observations, or even just thinking about how the system works. Second point there, a model's primary purpose, the very essence of a model, is to simplify and generalize and idealize. And through simplifying, to help us with our limited mental faculties to understand something in a better way, or to be able to explain it to a counterpart, communicate knowledge, even outside of research, communicate to end users of scientific knowledge, for example. Very essence of modeling, simplification. So the model is never true, but it can be a faithful representation of something that's essential or important or central about the phenomenon under study, about the carbon cycle of an ecosystem, for example. Some models, not all models, are suitable for making predictions forward in time, and that's often how we think about modeling, but there are many other ways models can be applied usefully in research and also across the science policy divide in talking with end users. And we'll see examples of many of those in this training course. Carbon cycling is an emergent property of land ecosystems, and for that reason we typically study the carbon cycle with a system dynamics framework, where the system is represented as stocks and flows, and those flows are biogeochemical flows of carbon, obviously, and potentially other elements as well as energy. And we've looked through the workflow of 6 steps that allow us to go from the question of a study to the answer using modeling. I hope that's been helpful for you, and I wish you a successful